I had a question for you all because I couldn't remember. This one drawback to, well, one drawback to two things. One drawback to having two Cal 2 classes, and then the other one drawback to getting old. So I can't ever remember what I told you, if I told you or if I told the other class. Did I show you this video earlier this semester with this professor? No, I didn't.
Professor ever? Is there?
Yeah.
The
The what? I don't even know if we're gonna have time, man. I don't see how we can get it in today. I mean, that's all we've got is today, right?
Yeah.
So maybe I might. I mean, it just depends if I have an extra 5 minutes or so. But yeah. Yeah. Negative 112. Okay, we have, let's see, it's not time. Never mind. I'll just shut up. Go. Y'all ready? You know, these markers, the ones that I'm going to use today are really good markers, but man, they are not easy to erase. And it was like breaking a sweat yesterday trying to erase on this damn board. I need like a buffer. All right, let me see here. So today we're going to try and do a couple of things. We're going to finish 8.7 and then go back and finish 8.6. That's our goal here. And I'm recording, so we can go ahead and get started here. Yes, I actually printed out your review right here. Thank you. Thank you. Thank you. Well, it's not problems, it's just topics. Yeah. It's better than nothing, though. And it says study your homework. Okay, it's time. So we're going to start out with finishing up 8.7. So look, the way 8.7 works, all right, with this Taylor-Maclaurin thing. Okay, when it comes to a Taylor series, if somebody asks you to find a Taylor series, you have to go through the whole process that we did in class where you set up that table and you take the derivatives and you try and find a pattern, all right? I think I'm going to try and do one more of those today. If you're asked to find a Maclaurin series, there's really two ways to do this. So if it's Taylor, you have to do a table, all right? Table, pattern, find a pattern, etc. Does that make sense when I say that? Okay, but if you're asked to find a Maclaurin series, you have two options. One is a table, pattern, etc., just like this one. Or you can use the formulas on page 484. And those formulas, let me make sure that is the page. Yes. Those formulas I will provide you on the exam, all right? Which means you do not have to print them, all right? So, during the test, when I ask you to find a Maclaurin series, I'm going to have to tell you which way to do it, all right? And the way I'm going to do this is I'm going to just tell you, find the Maclaurin series using, you cannot use the formulas, all right? So you have to do a pattern or something like that. These problems where you're allowed to use the formula are going to look something like, let me do one. I'm gonna do that by asking you to find something like this. find the antiderivative of sine of x cubed. All right, so if I ask you to find the antiderivative of this, you can't do it using any sort of technique of integration. So what you're going to have to do is get the Maclaurin series for this and then integrate the Maclaurin series, just like we did with e to the negative x squared. All right? So let's do this problem. That's where I wanted to start class today. We're going to actually do this integral. All right? And I'll probably say, give me the first 4 or 5 terms. Okay? So for this one, let's do that. Let's do 4 or 5 terms. All right? So I just want to be very clear with what we did last class, this section. There's really kind of like 2 main things. You're either going to be setting up tables or making tables and finding patterns, or you're going to be doing the formulas. All right? So to do this problem, we are going to now rewrite sine of x cubed using the Maclaurin series. So sine of x cubed, we found out last class that sine of x was equal to the sum n equals 0 to infinity of negative 1 to the n. I had messed that up, remember? And we fixed it. It's negative 1 to the n over 2n plus 1 factorial x to the 2n plus 1. Okay, that was our Maclaurin series for sine, which if you write things out, if I write it out, and the great thing about the table on page 484 is that it has this written and it has the first few terms written, I believe. I believe it does have it, but it does. Oh, just the first 4 terms? That's still good enough for you to get the pattern. Yeah. So this is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And you could keep going because we know what the pattern is, right? Dot, dot, dot. Okay, so that's what sine of x is. So what do we do to do that integral? Replace the x here. You can almost look at that x as like a u, okay? And so we're replacing that with this right here is all going to be replaced with whatever's being evaluated here inside sine, so x cubed, right? So this integral becomes the integral of, let's see, this, which would be x cubed, and then minus x cubed cubed, which is x to the 9th, because you're doing x to the 3rd raised to the 3rd, you multiply the exponents. Is that okay? X to the 9th over 3 factorial plus now x cubed to the 5th, x to the 15th over 5 factorial. And we'll just go one more, minus x to the 21st power. Y'all see what I'm doing? Yeah. Okay. Right? So x to the 21st over 7 factorial plus dot, 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 close it, dx. The thing is, this goes forever, right? But we've already established that, well, the whole idea behind the series is that you can go as far as you ever need to get within any precision you want. So that's good enough. And now we actually just find the antiderivative. So we do it term by term, right? Each one, boom, boom, boom. So what's the antiderivative of x to the 3rd? 1/4 x to the 4th. Now we are going to have a plus c out here, right? And it's kind of weird to do plus dot, dot, dot c, So a lot of times we put the c in the front, okay? C and then plus 1/4 x to the 4th minus, okay, what's this one going to be? Yep, 1/10, but you still have a 3 factorial down there. So how about I write 1 over 10 times 3 factorial, x to the 10th. So that's the antiderivative of this, plus 1 over, and I'll write, 16 times 5 factorial, x to the 16th. And one more term, minus 1 over 22 times 7 factorial, x to the 22, plus dot, dot, dot. Make sense? And that's it.
Are you going to give
Yes.
us any sorry.
For like factorials, do we just leave
You can leave them. Now this one is not too bad. Like this is 3 times 2 is 6, right? That's 60. But 5 factorial is starting to get bigger. 7 factorial is starting to get ridiculous at this point, you know? So I think it's easier just to leave it like this.
Are you going to give us any definite integrals?
I might. I mean, the question is, you know, what would be the big deal if I said go from 0 to 1 here? The only difference would be, you know, you would, at the end of this, you would put a bar, you put 0 to 1, right? And you wouldn't need the C anymore because the C would go away. So you plug 1 in and then you plug in 0, and it just, to me, that just seems like a waste of time. I'm more likely to give you just, now I want you to understand that's why we like this, because we can do a definite integral if we needed to, but it's really just one more arithmetic step that we're doing, so yeah, maybe not.
I was thinking like 0 to pi over 2, and that would kind of suck.
Yeah, no, we wouldn't, yeah, I wouldn't want to do something like that. Okay, we good? Is this clear? All right. Now,
Then you said 4 to 5. That's a good stopping point.
yeah, and I would tell you on the exam, all right? So I want to do another one of these, but this is going to lead us into the next topic that I did not cover in 8.7 that we need to discuss. All right? So how about we do this? How about if I ask you to find the antiderivative of e to the 2x times cosine of x squared dx. All right. Split what into 2? Into 2 integrals? That's right. Okay, so be careful with that. You're not allowed to split this into 2 integrals. That would have made life a lot easier for us a long time ago, right? Okay. So we cannot split this up. It kind of looks like integration by parts. Do y'all kind of see that? Problem is the x squared. Like if this was cosine x, we'd be okay, because then we could do integration by parts. And this would be that one, the rabbit out of the hat, where it would appear on the other side and we bring it over, and that was a long time ago. But we cannot do that, all right? So what I'd like us to do is I'd like us to use the Maclaurin series for this. But we run into a problem because, just think about this. This is the integral. E to the 2x has its own power series, doesn't it? Or its own Maclaurin series, yes? So that right there is like something, something, something plus dot, 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 right? Forever, that's what this is. And then times, this has its own power series, which is, you know, something, you know, plus dot, dot, dot. It's got its own thing, right? So how do you multiply 2 power series together? All right, so this is the thing that we haven't done yet. Adding 2 power series is easy because you just put a plus sign between them and that's it. It's just all the terms, and you could collect like terms. But how do you take 2 infinite polynomials and multiply them? So think about this. If I asked you to do like x squared plus x plus 1, let's say times x cubed minus 4x squared plus x plus 7. If I asked you to multiply those 2 polynomials, there's a procedure, there's a process, right? You start out with the first term, right? You go through to all of these, and then you move to the second term and you go through like this, right? Then you go to the third term and through, and then you're done, right? It would be, what, a total of 3 of these, 1, 2, 3, 4. It would be a total of 12 multiplications you would have to do, all right? And then collect all your like terms. That's if you have 2 finite polynomials. But imagine this, you know, was plus dot, 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 and this was plus dot, dot, dot. Then you run into a problem, don't you? Because you can never really get that first one to go all the way through because it keeps going. So how do we do it? Well, we're about to, all right? So what we're going to do is we are going to take this, rewrite it as its Maclaurin series, this, rewrite it as its Maclaurin series, and then we're going to try and multiply them, and then we're going to integrate that, all right? So we'll do the multiplication over here. We'll come back to the integral in a second. So first let's write down what is e to the 2x in its Maclaurin series. So you have to remember what the Maclaurin series is for e to the x. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x, right? Okay. But for us, it's not x, it's what? 2x. So it's 1 plus 2x plus 2x squared over 2 factorial. Yeah, you could put 2x over 1 factorial, but we don't need, yeah. Plus 2x cubed over 3 factorial plus 2x to the 4th over 4 factorial plus dot, dot, dot. That good enough? Yeah, I'll just do dot, dot, dot. Okay, that's e to the 2x. Now, again, on the test, when I ask you to do this, right, I'll say, find first 3 terms. Let's go 3 terms on this, because this is going to be pretty ugly. All right, first 3 terms. So that's e to the 2x, right? Let's clean it up first before we actually go and find cosine of x squared. So this is just 1 plus 2x plus, now what do we get there? 4x squared on top over 2, because 2 factorial is 2, plus 8x cubed over 3 factorial is 6. Okay, plus, let's see, 16x to the 4th over, what's 4 factorial? 24. Okay, let's reduce these fractions. 1 plus 2x plus 2x squared plus, what? Would what?
Like 4x squared over 2, is that?
No, because we got rid of the factorials. We turn these into numbers now, right?
Okay.
So I'm just making numbers out of these now. Is that? So this is what, 4/3 x cubed, and then plus last one, 2/3 x to the 4th plus dot, dot, dot. I forgot to put plus dot, dot, dot there. Okay, so that's what e to the 2x is. Now, what is cosine of x squared? So the Maclaurin series for this starts out where? 1, 1, 1, and then minus x squared over 2 factorial. So it's going to be x squared squared over 2 factorial. Do y'all understand where I'm getting this? I don't. If I'm moving too fast, you just need to let me know. You're okay? Plus, what's the next one? Should be x squared. So in the formula, it's x to the 4th over 4 factorial, right? But we're doing x squared to the 4th. So x to the 8th over 4 factorial. Let's only go one more. Minus x to the, so we're doing x squared to the 6th now, so 12th power over 6 factorial. Okay? Plus dot, dot, dot. Let's clean this up. 1 minus 1/2 x to the 4th plus 4 factorial is what? 24. X to the 8th minus, what's 6 factorial? Bigger number, huh? 120? No, then times 6, right? What is it, 7? 720? 7, I think it is. 1 over 720. Dot, dot, dot. Okay? Got that? Understand where we are? Okay, so what I need to do here is I need to go and try and find the antiderivative of this. So I need to multiply those together, don't I? Let's multiply those together before we do the antiderivative. And let's just do that right here. You know what? I'm going to do it right here. I'm going to take, so I'm not doing the integral yet, right? Okay, I'm going to take 1 plus 2x plus 2x squared plus 4/3 x cubed. I'm not even going to do the next term. I'm just going to do those because I only want the first three, right? So if I do the first four here, I should be good. And then here, I'm just going to do the first four, I guess. So times 1 minus 1/2 x to the 4th plus 1/24 x to the 8th. Let me just try the first three. I think I'll be okay with the first three. This one I'm not going to put in there. All right, you ready? Let's multiply. So what I would do, this is equal to, watch how I do this. First I do 1, right? And I pass 1 through here. And when I do that, I just get those three pieces, don't I? So what's the way I write this? 1 minus x to the minus 1/2. Try that again. Minus 1/2 x to the 4th. And then plus 1/24 x to the 8th. Look at all the space I left between these. You see all the space I did there? The reason I did that is because I'm leaving myself space for the missing pieces. Like, this is a constant. If I have any x terms, they're going to be here. If I have any x squared terms, they're going to be here. Any x cubed terms, they're going to be here. All right, so just, y'all okay with that just to start? That's 1 getting passed through, right? That's 1 going through. Now I go 2x through. So what would happen if I do 2x times 1? I get 2x. Now I'm going to put that, this is constants, these are my x terms, so I'm going to put 2x right here on a different row. Okay, what would my next term be if I do 2x times negative 1/2 x to the 4th? Negative x to the 5th power, because the 2 and the 1/2 cancel out. So I get x to the 5th power. I should put it right here. And it's plus, right? So plus, I should have put like plus 2x. What I'm going to do is add straight down when I'm done. I'm just kind of doing one row at a time. Do y'all get this? Is it negative? Hold on. Yeah, it is negative. Right here and here? Yeah, I don't know why I put that. Okay, good. Then this times this one, which is going to be a positive. 2 times that is going to reduce to become 1/12, right? 1/12 x to the 9th. That's over here, isn't it? Plus 1/12 x to the 9th. Now, I only need the first three terms, right? That's what I've asked for. So that means that I want any constant terms you have, any x to the 1st power, any x squared. So that'll be the first three terms. So all this out here isn't really going to matter at the end of it all. But let's just continue, all right? Now I'm going to pass 2x squared through. So what's 2x squared times 1? 2x squared. I'm going to put that right here. Plus 2x squared. So you can kind of imagine I've got constants here, I've got x terms here, x squared terms here, x cubed terms here, x to the 4th, x to the 5th, right? So on and so forth down here, and I'm just lining them up. What's my next term? 2x squared goes to here, right? So minus x to the 6th. And I could probably stop there, right? Because anything else that comes out here is going to be too far away. Do y'all get that? Now, if I ask for the first 8 terms, then yeah, you would need to keep going out. I'm not going to do that. But you get the idea that I'm just interested in these first 3. So I just need to make sure that as I continue through here, I'm not going to get anything else over here. Okay? So let's see what happens. On the next piece, I would be going this times 1, right? Which would be 4/3 x cubed, which would be right here. So plus 4/3 x cubed. And then as I move this through, all of those powers are going to be bigger than x cubed, aren't they? So I know I don't really need those. Do y'all get that? Yeah. So can you see that right now, my first 3 terms is this, this, and this. These 3. And then I'm never going to get anything else under here, right? Because as I move out this way, these powers are going to start getting bigger, so there's no way I'm ever going to pick up another x cubed or an x squared or an x or constant. Yeah? So, we're done. We're ready to integrate this now. So the antiderivative of this would be the antiderivative of 1 plus 2x plus 2x squared plus dot 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 dx. Y'all okay with that? See, I'm only doing the first three terms. I'm really lucky here. Just for the sake of demonstration, what would happen if we had done this and on one of our multiplications we would have got, let's say, like a minus 5x down here on one of these rows down here. Then we would add them together and we would say negative 3x. Okay? So like you would look and say, oh, I've got two things here, so I've got to add these together. Negative 3x would go up here.
So is that way you could check if anything would interfere with the other terms?
Yeah, because I want to make sure I'm not ever going to pick anything else up down here, right? Because I'm combining these. I'm trying to add all these together, right? So I'm kind of like going down column by column saying, you know, how many constants do I have? How many x terms do I have? How many x squared terms do I have? And so on and so forth. Yeah. All right. What's the antiderivative of that? Yeah. C plus x, right, plus x squared plus 2/3 x cubed plus dot dot dot. Okay? That's it. So I'm going to go now to Wolfram Alpha, the almighty Wolfram Alpha, and I'm going to ask it to integrate that for us. Integrate e raised to the 2x times cosine of x squared. And look at the, well, there, down here. Can you all see that down here? So what is it? Like 1/4, the fourth root of negative 1, e to the negative I pi. Oh my goodness. Error function. This is an error function. So erf I is the imaginary error function. I mean, this is crazy, right? That's basically telling you there's no way to do that antiderivative by hand without series. So if we scroll down further, it's got more mumbo jumbo. I thought for sure it was going to have a series here. Maybe I didn't go far enough. Huh. Interesting. I didn't see it there, did you?
So if we had like a comprehensive final and you just put that problem on the board, you know, on the paper, on the test, some people would go to by integration by parts, but
I would hope not, but yes. Yeah.
there would be more. We would have to know that it's power series.
Yeah. Yeah.
Because you can't do integration.
So I went back to Wolfram Alpha and I typed in, give me the series for that. Okay? So there you go. You see the series? That's what we got, right? And now you can integrate that. I'm surprised that it didn't, when I asked it to integrate, I'm surprised it didn't show me the power series. So here's this, look at what it says, series expansion at x equals 0. That means it's Maclaurin, right? This is your Maclaurin series. Now it says Taylor series, but we know that Taylor at 0 is Maclaurin. So this is your expansion. We got those first three terms and then we integrated that. See that? Okay. When, what? We didn't go that far. Yeah, see, on the next multiplication, it would have been this times 1, and we would have got this one, okay? But for the next one, for the fourth power, we would have had one here, and there would have been another one down here that we would have had to add together. We just didn't go far enough out in our multiplication. This would have appeared again. We would have had another x to the fourth term. And then when we add them together, you would have got this. Did you try and go further on yours? Yeah. Double check it. I mean, you should get a second term there. Okay.
How close would this answer be to something that like we already know how to integrate?
How close would it be to some? I'm not sure what you mean.
So, I mean, like, something that we could solve with integration by parts and new stuff, if we did it in power series, would we have to go out like really far to be able to make it look?
Okay, so what you're talking about is something in this section that I actually don't cover, and that is how far out in the series do you have to go to be within a certain error, right? And that has to do, there's a lot of things at play there, but every series is different. Some of them get converge to the answer faster than others, but there's a way to check it. And if you're more interested in reading about this, I don't cover it because, well, I mean, shit, we're already out of time. You know what I'm saying? Like, we don't have the time for it. But where is it? Taylor's formula.
It's okay.
Yeah, I'm not sure exactly what page. I think it's in 8.6. But we have an error formula that tells us, okay, if you stop at the 10th term, let's say, right?
S minus.
Yeah, then it says, you know, like how much error is there? How much off are you from the true answer?
Okay.
Yeah. Okay, moving along. I'm not going to do this problem complete. Well, no, I am going to do this one. Sorry. All right. I would like us, for this one, I'd like us to do find the first, let's say, 4 terms of Maclaurin for f of x equals tangent of x. So tangent of x is not on page 484. So page 484 has Maclaurin series, right? The common ones. And tangent of x is not there. Now arctangent is, it happens to be there, but tangent's not. So how would we set about going and doing this? Well, you have 2 options. Make a table, take derivatives, try and find a pattern, right? That's one option. The other option is to use Maclaurin series, the table. But I just said it's not on the table, right? But tangent is sine divided by cosine, isn't it? And you have Maclaurin series for those. So the question becomes, how can you divide 2 power series? We just multiplied 2 power series, right? How do you divide them? So wouldn't that be the same as, okay, what's the Maclaurin series for sine? No, just like give me the first like 4 terms of sine.
X minus x cubed.
Okay, so it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. That good enough?
Yeah.
Plus dot, 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 over the power series for cosine. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, dot, dot. All right. How do you divide 2 power series? Well, how do you think you divide them? Long division. Long division is how you divide them. So we've got to do long division. So here's how this is going to work. I'm going to put a long division box over here. Okay. What goes on the inside of the box? The numerator. X, let's do this, minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Notice my gaps. Do you see the gaps I've left there? Those are for my even terms if I have them, right? And I know I'm going to have them. I think I'm going to have them because I've got a cosine out there. So on the outside of the box goes cosine, right? So when you do it on the outside of the box, you know, you're going to write out here 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, 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 right? All right, I'm going to go get a little bit of water in this thing. Just see if you can't figure out what you would do next. I mean, long division is long division. There's nothing special we're doing here. Hey, Greg.
I really thought that was a 0. And that's an 8?
I'm going to steal a little bit of this juice. Is that okay?
Hey, there's some really dangerous stuff right there if you want.
What's that? Oh, in there? Is that what you're using?
Yeah, you can probably start a car in there.
Turpentine or something? So what are you asking yourself for that first part? What are you saying to yourself here? Well, I'll tell you what I say to myself. I say, what do I multiply this by to get that? X, right? So I'm going to start with an X. And I put that X, I can put it anywhere up here, but I'm just going to put it right here. So X, and then what do you do with that X? Multiply it times here, 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 and put those terms underneath here. Okay? And then we'll have to change the signs and add down. So when I do x times 1, I get x, right? And then I do x times this, which gives me negative x cubed over 2 factorial. Negative x cubed over 2 factorial. That's going to line up in my x cubes. Negative x cubed over 2 factorial. You with me?
Yeah.
Then I do x times this one, which is going to give me positive x to the 5th over 4 factorial. And then the last one, minus x to the 7th over 6 factorial. Right? Okay, then come through. Change the signs. This is going to become minus. That's going to become plus. That's going to become a minus. That's going to become a plus. And now you add straight down, don't you?
Yeah.
So when I add down, these x's cancel. And then I have to add these two together. That means you have to have the same denominator. So this is really, what's that? That's really negative x cubed over 6, right? And this is really plus x cubed over 2. So common denominator would be 6. So I have to multiply this on the top and bottom by 3. Agreed? So this would be 3 over 6. And now add them, what do you get? 2x cubed over 6? Yes? Which is? 1/3 x cubed. This is going to start to get kind of messy here. Do you see how this is going to get messy really fast?
Yeah.
Okay, this is x to the 5th over 5 factorial, which I believe is 120, right? And this one is x to the 5th over 4 factorial, which was 24. So now you got to get a common denominator between these, right?
Both sides.
And then you bring it down here, it's something, and this is something, right? Understand? Now you go to the next step. That was just the first term. So now what do? You ask yourself, what do you multiply this by to get this? 1/3 x cubed. And then what do you do with that 1/3 x cubed? Multiply it here, here, here. Oh shit, right? And then put that down here and subtract. And I mean, there's no way around this. This is just ugly arithmetic, right? Yes.
Eric, wouldn't it be easier just to build the Maclaurin series like we did for sine and cosine?
Sure. It might be easier to make the table. The important part of this is for you to understand this is how we divide 2 power series. It's not pretty, but this is how we do it. All right?
That's just for like 4 terms.
I only got 2 terms, right? I only got 2 terms, and I actually didn't do these yet. So to get a third term, I'd have to do these, and then I have to do even more, and it's going to be messy. I'm not going to do it, okay? I would not ask you for 4 terms on the final, okay? I'd ask you maybe for the first 2. I'd make sure that I've worked it out myself and that, you will have to do this, okay? You will have to like get a common denominator maybe once or twice in the problem, okay? So just be prepared for that. Does that seem reasonable?
Yeah. I mean, if there's like one.
If there's one of those, yeah. Okay, so multiplying power series, would you agree was easier than this? Okay. So I want to show you something now. Came across this video on YouTube years ago. I'm going to share it with you now.
YouTube is a wealth of knowledge.
All right, and hopefully we can get the audio here. Let's see.
You are not happy with the series.
Okay, so this is only a minute 29 long. Okay, so let's just kind of. I'll try and translate. Okay, I was going to have it closed caption, and YouTube thought he was speaking Russian. So just watch and we'll talk. All right, I'm going to start at the beginning.
It seems that you are not happy.
There we go.
Going on. It seems that you are not happy.
Oops.
You are not happy with the series. How you multiply the series? But let's see now some other example. What I can do?
Just wait. I'll translate in a second. The camera's going to move, so.
Multiply.
What do you say? Okay. Just listen.
What exactly? How? Let's see.
Y'all just listen. I want y'all to listen.
From here to here.
Yes.
Oh, you can divide one.
No, that's why I wanted to.
Why not?
Could you do it manually? It doesn't work. It doesn't make any sense.
Okay, let's go for
Why are you answering my question? That doesn't make any sense.
you are doing this.
You don't answer anybody's questions.
Okay, let's go on this. So,
Okay, so that's the video.
it seems that you
That's-
are not happy.
That's the video. All right. So I made my own response to this video because off the chalkboard, the student was asking how you got from here to here, and his answer was, you divide 1. You divide 1 by what? By the series. Okay? 1 divided by this series yields this. Here's the work. 1 divided by that series with all the work gives you that. The student said, do it manually, it doesn't work. Right? It works. The student didn't know how to divide a series. That was the problem. Now, I don't agree necessarily with the professor's, reaction was just like, whatever. But in this class, he assumed his student could divide series. Yes, you got through Cal 2. This should not be like you telling the professor that the math is wrong. You understand? That's what the student was doing. He's telling them that the math doesn't work. It works perfectly fine if you know how to divide a number by a series or 2 series, right? That's what if you look at the board again, it was all just series everywhere, right? So I just don't want you to ever walk into a class and be like, yes, we could have done tangent a lot easier, maybe, right? But you need to know how to divide 2 series. It's more important. And also, we understand the amount of work that's required for this. And do you see that on the board? It was just 1 line, right? 1 line to the next line. That's all it was. So there's always, as you move up, as you go from one line to the next, when you're getting notes from a professor, a lot of times that one line has a lot of work behind it, right? That's not shown. So if your question is how do you get from one line to the next, you need to make sure you go off, you know, with your study partners or whatever, or go get help tutoring, whatever, or you sit down, you try and figure out how are they getting from that line to the next one. Because most likely, if you've got a professor up there that's working off of their own notes, like this professor was, I'm pretty sure he had his own notes.
Yeah, he looked at the paper.
Yeah, so if you've got someone up there who's, well, this guy's definitely done this before, you can tell he's been there for a while, right? And he's working off his notes. When he first asked, the student asked, you know, like, he looked up at the board, the professor, and was like, this to here to here. He actually looked at it. He wanted to make sure he didn't write something down wrong, right? But then he just said, no, it's right. He looked, and he's like, that's right. Those notes, I mean, they have been vetted, okay? In other words, they've been scrutinized, and all the errors have been fixed. So don't ever assume, I mean, you always want to be skeptical, but don't be arrogant. You know what I'm saying?
Yeah. I mean, if anything, if he was that confused, he could have like gone after class and like, hey, this doesn't make any sense.
Yeah, it's a different environment. You know, it's a different environment. It's probably a university setting, and it's probably, you know, yeah. Well, anyway, so the comments on here are hilarious. If you go to the comments, you know, you can imagine that half of them are like, this is why I hate college, you know, blah, blah, blah. And then the other half are like, just freaking learn how to do division of series. Hello, you know? So it's a mixed bag. So, I don't know. Yeah, we'll see what the top comment is.
Yeah.
Let's see here. These students are morons, and they're going through college without paying attention. Do they forget everything from one semester to the next? Polynomial series are taught in the first semester. When solving integrals, it is crucial. Let's read this. I like that one. It is crucial to have a lot of math skills to be able to translate a math expression into another that is easier to integrate. Hello, that's what I'm talking about, right? At some level in college, it's absurd to teach people the basics. Right? I mean, so now look, I understand the mechanics. The mechanics aren't necessarily easy. It's not trivial to do the division. And the fact that it's up there on the board going from one line to the next is not, oh, you should be able to do that in your head. That's not what that is. That's just like, look, like this becomes this. We don't have 30 minutes to do that division. You know what I'm saying? So what's more important is the bigger picture of the problem that's going on. All right? Okay, so here's one on the other side. There do exist teachers who are not qualified to teach. They're boring, unimaginative, and teach by rote. I've had some pretty amazing instructors in confusion. Yeah. Okay, anyway, it is what it is. Let's move on. So that's going to wrap up 8-7. All right? I think, yes. So 8-7 in a nutshell, you have Taylor series, right? Maclaurin series. You might have to do tables and figure out patterns, or if the Maclaurin series comes off of our little chart, then you can use that. You might have to multiply and divide series, right? So the homework now can be completed. Now, would you like me to do one more Taylor series, or did anyone do the homework for Taylor series? Yeah, do you feel like I need to do more, or do you think the homework was thorough enough? You're okay? Yes? Okay. Because I'd prefer to go back to 8-6. Why not ask you? I did ask everyone else. You answered. And if you haven't done the homework, then you aren't qualified to answer the question. You know, so if you've done the homework for 8-7, I believe that within the homework it fills in any holes that I have not talked about here. Some of the Taylor series, when you create them, finding the pattern is not as simple as what I've shown in class. Some of them require a little bit more thought. Yes?
For like, I don't know, I think it was like the first couple of problems on the homework
Mm-hmm.
we did.
Cosine sine.
Yeah, no, like on the table,
Mm-hmm.
it wouldn't skip, like it wouldn't have zeros for some of them, so we would just put it over n factorial.
Mhm.
But when they had zeros, we'd have to write out like the whole
Yeah.
thing, and then figure out like
What the formula was from that?
Exactly.
That's because if you get skipping,
You got to figure out.
then you got to figure out the formula yourself. If it doesn't skip, you can go straight to it. It's a little weird.
That's what I figured out. That's
Yeah.
Oh, that's cool.
Yeah. Yeah. Maybe, you know what? Let me do 8.6. If we have enough time at the end, I'll jump back and try and do one problem from 8.7. All right. So 8.6, you probably have forgotten this now, but let's try this. Express as a power series. I'll tell you another story about bad professors real quick. I had a professor in college, in graduate school, who was outstanding. Now, my definition of outstanding is different than what you would probably think. This man would come in, he wouldn't say a word to us, he wouldn't look at us. All he would do is take his notes and write them down on the board. You couldn't ask questions, he just took his notes and wrote them down. And we just sat there and copied them. And that was it. And then we had to go home and take those notes and try and make sense out of them. And I learned so much because his notes were so good. They were just such good notes, right? And I learned a lot about teaching myself math that way. So anyways, this guy gives us a take-home test, all right? Which in graduate school, almost every test was take-home in math, all right? So I get this take-home test, and I'm about 3 weeks into this thing, right? So I put a lot of time into this, and I think there were 4 problems, and on the third problem, yeah, these were long tests, right? There was just a few problems you'd have to do proofs or something like that. So I had this one problem, and it was basically like, you know, if this is true, then show that this is true. So I went and I tried to prove it, and I finally got to the point where I could find a counterexample. So in math, whenever you have a proof, like if you're going to say, like if P then Q, right? If you're going to do this in math, then if you're asking if this is true, then one way to disprove it is just to find a counterexample. So like if I say right now, everybody in this room has glasses on, right? Is that a true statement? Does everybody in this room have glasses on? I could find a counterexample, right? If I just find one person without glasses, that statement's false, right? That's called a counterexample. So the professor had given us a thing to prove. I actually found a counterexample which showed that that couldn't be proven. Does that make sense? Right. So you have to know a little backstory. This is the same professor that I had for another class, and a student raised his hand in the middle of the class and asked him, why do we need to know this stuff? And he took the student out and took him to the registrar and dropped him from the class and came back to class, okay? So I've got this take-home test that I've had for several weeks. I've got a problem he gave us, and I believe I've come up with a counterexample that shows that that proof cannot be proved, right? So I like very nervously walk into his office, you know, and I'm like, you know, I'll tell you, Dr. Wilson, who cares? So I walk in there and he's just, you know, kind of looks up from his desk, kind of annoyed, you know, like, what? You know, and I walk in there and I lay the test down. I'm like, this problem 3, you know, you asked to prove this. I believe I've found a counterexample that shows that, you know, blah, 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 blah. I said, now, however, in the theorem or in the problem, if you change that, you know, m is equal to 3 instead of m is equal to 4, then it would work, and I could prove it, and it would be fine. And he picks up the test, he looks at it, he says, oh, that's a typo. That should be a 3, or whatever. And I was like, and he's like, go tell the rest of the class. And I was like, are you kidding me? You know, like all that time, all that effort I'd put into that problem, and it was a mistake, a little typo by him, you know? But I learned, I knew that proof better than I would have ever known it had that typo not been there. Because I had to disprove it, right? Like I had to walk in there and know my math was solid, that he couldn't challenge me. Like, you know what I mean? Like, I was nervous, but I felt so confident about it that it wound up being a great experience. So I guess my point is typos, right, in math, like if a professor puts something on the board and there's a mistake, like that happens, obviously, hopefully you can learn the material to a point where you see the mistake, you realize, you know what I'm saying? Or, whatever, okay. Power series.
Did he drop you?
He didn't drop me, no. He liked me, actually. He liked me. I think he respected me, which was good. I think I earned his respect that day. Okay, expresses a power series. So we're back to 8.6. Okay, so we're back to 8.6, and we're trying to use this whole idea that if we have 1 over 1 plus x, that will be equal to the sum n equals 0 to infinity of x to the n, so long as the absolute value of x is less than 1. Do you all remember this? Right, this thing? Minus x. I don't know why I put plus x. Minus x. All right, so we want to try and use this to do this. Now, we could do Maclaurin series. If we're doing 8.7, right? We could do Maclaurin series here. But I want you to see something. That's why I'm doing this problem back in 8.6. I want you to see something. So right now, this and this have nothing to do with one another, right? I mean, you look at that, they don't look the same. However, the derivative of this is 1 over 5 plus x. Now, I could write x plus 5, flip it over, right? But I did it 5 plus x because I want it to kind of start to look like this. Now this is 1/5 times 1 over what? 1 plus, I'm factoring a 5 out of the bottom to get a 1 like this. 1/5 x, right? And then I'm going to do minus minus on the next step. 1/5 times 1 over 1 minus 1/5 x. Did y'all see all that? This cannot be rewritten using this. However, its derivative does look like something like this, right? And so if I wanted to, I could rewrite this as some what? N equals 0 to infinity, right? No. N equals 0, I almost did it again. N equals 0 to infinity of what? Negative 1/5 x to the n. So this becomes this so long as what? There is a condition here. The absolute value of negative 1/5 x must be less than 1, so the absolute value of x must be less than 5. So just, bring this negative 1/5 out as a positive 1/5, multiply both sides by 5, and you get that. So I am allowed to go from here to here so long as that's true. And that's just using this same conditions here. All right? You all right with this? Now I'm going to rewrite that a little bit. This is going to be 1/5 sum n equals 0 to infinity of negative 1/5 to the n, x to the n. Right? Separated it, split it into two. And that's because for power series, this is my c sub n, and this is my x minus a to the n. So now I have c sub n and x minus a to the n separated, right? Any questions on this? Okay, is this the power series for this? No. That is the power series for the derivative of that, right? So if I want to go back to this, what do I have to do? I have to integrate that. So this function should be the antiderivative of 1/5 sum n equals 0 to infinity of negative 1/5 to the n, x to the n dx. Make sense? It's like we took the derivative so that we could get a formula, and then we antiderivative to take it back to the original function. It's kind of weird, but that's what we're doing.